In today's video, we're going to be talking about half-life. After watching this video, you should be able to have an understanding of what a half-life actually is, and then be able to use the half-life equation to calculate how much of a radioactive element is left. Okay, so let's get right to it. This is just, again, a kind of a recap of the last couple lessons that we've been talking about in terms of nuclear physics. Elements that are radioactive are unstable, and the very reason that they are unstable is that nuclear force that actually holds that nucleus together is unable to hold it together. Basically, the electrostatic force is overcoming that nuclear force and causing it to break apart. As that radioactive element shoots off particles, it starts to change to a different form. Okay, so basically, in the end, nature is trying to get these elements to become stable. It doesn't like that they're unstable. And so the amount of time it takes for half of that amount of radioactive isotope to decay, so if you've got this big old pile, let's say 10 pounds of it, the amount of time it takes for half of it to be gone, or not really gone, but change forms, is called the half-life. Okay, that's what is referred to as the half-life. And so here I have an example of what a half-life is. Let's say I have 10 grams of a substance, and I know that the half-life of this substance is 1 hour. So let's say I take this 10 grams, I watch it for 1 hour, 1 hour goes by, how much of it do I have left? Well, according to what this thing is telling me, it tells me that I'm going to only have 5 grams of that substance left. Basically, the other 5 grams have changed into a different substance. It has gone through one half-life. Let's say I sit there for another hour with my 5 grams of substance, and I measure how much I have left after another hour has passed. It turns out I only have 2.5 grams left of that substance. Okay, so these are all just half-lives. You have one half-life passes, then another half-life passes. Basically, it's the amount of time it takes for half of the substance to change forms. Okay? Some terms to be familiar with, and where these terms show up will be actually in the equation that you're about to see. N stands for the number of nuclei remaining after a certain amount of time has passed. And sometimes that time is given to you in hours, sometimes it's years, sometimes it's given to you in half-lives. But N is the number of nuclei remaining after some amount of time has passed. N sub O, or what it's typically referred to in physics as N sub naught, this O here, is the original number of nuclei, how much you start with at the beginning of this experiment. And it's always going to be bigger than N. And the reason why is because it's the thing you start with. Okay, so you start with some amount of substance, and then after some time passes, now you have this new amount of substance, and that's this N up here. Okay. And A stands for the radioactivity of the sample. The unit of A is called the becquerel, and basically what a becquerel is, it's the amount of decays that happen per second. So something that's really radioactive will have a lot of decays per second compared to something that's not very radioactive. So the more radioactive a substance is, the more dangerous it actually turns out to be for humans because it's undergoing these decays at a much more rapid rate. And I think that kind of makes sense if you kind of think about it. So here we've got those terms to be familiar with. Let's take a look at them in our formula on the next slide. This is the formula that you may have to end up using, and it basically what it is N equals N sub naught times 1/2, and then that's T time in the exponent spot. Okay, so the amount of radioactive isotope remaining in a sample equals the original amount, which is N sub naught, this guy right here, times 1/2 to the T, which is going to be the number of half-lives that have passed. That's what little t is the number of half-lives that have passed. Okay, and that, if you calculate that in your calculator, it will give you the amount of remaining atoms left, okay, how much of that substance is left. So if I were to ask you, I have 10 grams of a substance and it has undergone, 6 half-lives, how much of it's left, you would be able to actually calculate that by using this equation. And it certainly is calculator work. When you start using exponents and that kind of stuff, I don't expect you to do that in your head. It's something you just throw through a calculator and it gives you an answer. Okay, so it's a pretty straightforward equation, really, if you just kind of think about what these things mean. 14, you're just going to be plugging numbers in to find an answer. This is just a quick little graph I'd like to show you. Carbon-14 is something we typically will date substances with. The reason why is because it has a half-life of 5,730 years. So that kind of turns out to be useful if we're looking at, you know, I don't know, various fossils or that type of thing that we find in the earth, that archaeologists find in the earth. And this is just a little graph showing you how much carbon-14 is remaining, what percent of it is remaining as it goes through various half-lives. So here we have 100% at the top of our y-axis, and after one half-life has passed, you'll notice we have 50% left. After 2 half-lives have passed, we now have 25% left. After 3 half-lives, we have 12.5%, and so forth. You'll notice that this graph actually starts to just even or kind of flatline out. Okay? In theory, you never completely get rid of the radioactive substance. It continues to go on and on and on. That just keeps getting smaller and smaller and smaller, but it never really completely goes away. But that's really beyond the scope of this lesson. Okay, so hopefully that gives you a general ballpark idea of what a half-life is and how you can use it in a formula. And that actually takes care of this video. I will see you guys next time.